full of nonsensical, non-coordinated nonsense. There's, it's coordinated, it's got no coordinates. That doesn't, something seems wrong about that. Well, you can do that here too, but with meaning.
But instead we could just not have coordinates at all.
All right, I'm going to get started here once I get this mess off this board. Sorry I'm late. I foolishly tried to print something in the printer, only to find out that it has a insurmountable problem. I told the secretary, there's something wrong with the printer. She's like, yeah, I know. I'm like, uh-oh. Secretary's just like, yeah, whatever, it's out of my hands. Like, that's a bad sign. That means it's a bad one. Anyway, I'll start. Dear Father, we thank you for this day again. I thank you for these students and just ask you to bless this class, Lord. In your name I pray, Lord Jesus. Amen. All right, so we've now entered the next story arc of this course, which is, largely speaking, the Jordan form. And to motivate this part of the course, it's all based on one simple question, which is, can you diagonalize a linear transformation? So in other words, we're going to talk about diagonalization and eigenvectors today. But before I even get into that, let me just remind you like what we're up against here. So here's the story. For us, V is going to be finite dimensional, all right? So you have a finite dimensional vector space, and you've got some basis beta, say V1 through Vn, right? And you've got some linear transformation T to the vector space again, and you're still using beta here, you're using beta there, beta everywhere, all right? And so this is the situation. Then if we look at, the coordinate map with respect to beta, that takes us down here to Fn. Likewise over here, right? And then we can talk about left multiplication by the T beta matrix, right? And, excuse me. So, we've described how to calculate that thing. You've done it a few times. What happens if I choose a different system of coordinates, right? What if I choose, phi beta bar here and here, right? Right? Then how's this mapping here related to that one, right? So let me not do all the calculations today because I already wasted 2 minutes on the printer, but remember it's a simple exercise to work out that this is equal to P inverse times the matrix of T with respect to the beta basis times P again, right? This is the theorem, the coordinate change theorem. And those coordinate change matrices, we could make precise. There are particular, mappings between the beta and the beta bar coordinate systems, right? So this relation, more generally, definition, if we have A and B in Fn by n, then A is similar to B if and only if there exists G in GLN F. And that, by the way, is the set of like G in Fn by n such that the determinant of G is not equal to 0. I don't know if I've used that notation in here before. I guess I haven't. That's the so-called general linear group, the general linear group of n by n matrices over the field. simply the set of all determinate non-zero matrices, right? Those are the invertible matrices. And A and B are similar if, B is equal to G inverse AG, like that. That's our definition of similarity of two matrices, right? So what this little calculation over here that I've half done shows you is that if we look at a linear transformation and we look at its matrix, right? And then if we look at that matrix, if we look at that transformation with respect to a different choice of basis, then our two matrices are similar to one another, right? So the matrix of a linear transformation with respect to one basis and the matrix of the linear transformation with respect to another basis, these will be similar. Now this presupposes that I'm using the same basis in the domain and the codomain, right? If we're allowed to change the basis in the domain and the codomain separately, then we can do the straightening theorem, right? There's much more freedom there. But here, this is the question, is when are two, another way to look at this question is, if I give you two square matrices, when are they similar, right? At the start of chapter 5, I proved to you basically there that that question is tantamount to asking the similar question, when do you have two linear transformations? Are they really the same transformation? It's just a question of like changing coordinates and they have the same formula, right? A linear transformation from a vector space to itself. And so essentially the answer is, well, they've got the same formula if the given transformations have matrices which are similar with respect to one choice of basis. I prove in the start of the chapter if the two transformations are similar with respect to one choice of basis, I prove that they'll be similar with respect to any other choice of basis actually. So similarity is something that works like that. I was reading the notes. I noticed something that I have failed to define. So let's do that before I forget. Definition. And you guys tell me why these are good definitions. The determinant of t is equal to the determinant of what? And the trace of t is equal to the trace of what? Because the standard matrix, but that wouldn't make sense here because t is a linear context, fair enough. T is a endomorphism, a linear transformation from V to itself. All right, that's what I'm talking about here. How do I define the determinant? And I am assuming finite dimensional. We'll keep it finite in here for a bit.
Would it be the left multiplication of t with respect to any basis?
Kind of, sort of, but I'm going to be a little bit more direct, so it's just this. And why? No, so like anytime you make a definition which uses a basis, it begs the question, is this a good definition, right? Because what if I changed the basis? What if I picked a different basis? Would I get a different determinant? Would I get a different trace? Well, that would be embarrassing, right? But that doesn't happen. Why? Because this is how the matrix of the transformation with respect to different bases are related, right? So if I was to do, determinant of P inverse T beta beta, right? P, well then by the properties of determinant, that's the determinant of P inverse times the determinant of the T beta beta matrix times the determinant of P, right? But you can take these two things, put them back together, and you get the determinant of the identity, determinant of T beta beta. So what you got? Well, you just got the determinant of T beta beta, right? Well, excuse me, beta bar, my bad, this is, oh, well, yes, fine. This is fine, that's what I meant. But this is literally the determinant of T beta bar, right? That's the coordinate change formula. So the determinant of similar matrices are equal. And the similar calculation goes through for the trace. So we can define the trace of a linear transformation or the determinant of a linear transformation simply by calculating the determinant or the trace of a matrix with respect to any basis you like. All right? Okay, so there's that. definition. T is diagonalizable if and only if there exists basis beta, basis, oh no, rats, basis for V such that the matrix of T with respect to basis beta is, you know, diagonal. So I guess I could write it diag, you know, D1, D2, Dn. It's a diagonal matrix, right? Likewise, A in Fn by n is diagonalizable if A is similar to, let me call this thing D. If it's similar to a diagonal matrix, all right? Now, so let me just get straight to the point. As soon as you're looking at a diagonal matrix, you really should start to think about eigenvectors if you look at what's going on, right? Because, you know, what does this mean? This means what? This would mean that, you know, T of V1 is equal to D1 V1, right? For one thing, because like the first column is D1 0 0 0, and it would mean that T of V2 is, you know, D2 V2, etc., right? Working back through the coordinate map, right? So maybe you remember from 221 that this is what we want for an eigenvector, right? Let me make the definition though so we can be sure we understand each other. So definition. T, going from a vector space to a vector space, a linear transformation on, you know, vector space V over F. The field matters here, so let me say that over F. Then V not equal to 0 is an eigenvector with eigenvalue lambda in F if T of V is equal to lambda V. Likewise, you know, x not equal to 0 with ax equals to lambda x for lambda in F makes x an eigenvector for a n by n matrix in the field. And then finally, a basis of eigenvectors is called a what? Yeah, a basis of eigenvectors is an, as you said, eigenbasis. All right. So, So I would say that it's pretty much an immediate consequence of the definition of diagonalizable, that if a linear transformation is diagonalizable, it has an eigenbasis. See, because if you say that beta is a basis that makes this happen, that makes everything in the basis an eigenvector. Therefore, it's an eigenbasis. Of course, the deeper question to ask is this always possible, right? Can we always find an eigenbasis for any transformation? And perhaps you remember the answer is no, right? So we need a method to understand when we have an eigenvalue, when we don't. And this theorem is pretty much where it's at. So this is theorem 5.1.3, if I can keep from coughing. And let's see here. Huh. Right, fine. So in these notes, I can't make up my mind if I want to work with matrices or with transformations. So I kind of hop back and forth. And so, like, to be fussy, we should be able to give the proof in either formalism. But pretty much if you can prove it in one formalism, then you can transfer it to the other. But anyway, so let A be an n by n matrix, then lambda in F is an eigenvalue. If and only if what? The determinant of A minus lambda I is equal to 0, right? So how's the proof of that go? All right, so proof, this is a, so we'll go this way, right? If, AX is equal to lambda x for some x not equal to 0, then we have A minus lambda I times x is equal to 0 for x not equal to 0, right? Thus, A minus lambda I inverse does not exist. Because why? Well, we have a non-zero solution to the homogeneous problem, right? I tried. In other words, another way to think about it, the non-zero x means there's a linear dependence amongst the columns of the matrix A minus lambda I. So it can't be invertible, right? So it must be a determinate 0 matrix. And so there you go. And to go the other way, it's almost the same thing. I mean, if the determinant of A minus lambda I is equal to 0, that means that A minus lambda I inverse does not exist, right? Which means that A minus lambda I times x equals to 0 has x not equal to 0 solution. And so we're done. That's an eigenvector. You guys look bored. I'll try to do something harder. Now, let's just work through something here. So if we have T, a linear transformation from V to V, right? Then if T of V is equal to lambda V, that tells us what? That the coordinate of T of V with respect to the beta basis is equal to the coordinate of lambda V with respect to the beta basis, right? But this means that T beta beta times the coordinate vector of V with respect to beta is equal to lambda times the coordinate vector of V with respect to beta. So what am I saying? I'm saying that there's a kind of an obvious lemma here. And I'm not sure that this lemma is ever stated formally in my notes, but it probably should be, which is that, T has eigenvalue lambda if and only if, T beta beta has eigenvalue lambda. See, the thing is, I started this calculation in the way that I did, but it's reversible. This is actually a reversible calculation, right? I can just as well do this because the coordinate map is an isomorphism. It goes both ways. So, in fact, we can look for eigenvalues for the linear transformation, or we can look for eigenvalues for the matrix of the linear transformation. These are part and parcel of the same thing, right? So, here, and we're gonna want to look for a determinant of T minus lambda times the identity map on V equals to 0. And I may just choose to rewrite this as just T minus lambda for the sake of brevity. Understand that minus lambda in that context is understood to be, the multiplication by lambda map. All right. Oh, actually, I do have this stated as a corollary. That was corollary 5.1.4. And that brings us to a definition, which is the characteristic polynomial. So, oh man. I think this current cough, it's not the same like sickness I had. I planed a bunch of wood this weekend without a mask, and so I think I may have inhaled a little bit too much dust, and that's what I'm currently suffering from. I'll get better eventually. Okay, so where was I? Definition, characteristic polynomial. The characteristic polynomial of A, and of course this, is, as usual, is an n by n matrix, is P of S equal to the determinant of A minus Si. Likewise, the characteristic polynomial of T and endomorphism on V is P of S equal to the determinant of T minus S. All right. Or if you want me to be more verbose, T minus S times the identity on V. There you go. I've been very obnoxious. These are the characteristic polynomials. All right. So I should just make a comment here that because we're working on an n-dimensional space and we know how the determinant works, right? It will give us an nth order polynomial when we work out the details here. So we know that we can anticipate that P of S, generically speaking, has the form minus 1 to the n, t to the n. Oh man, t to the n, listen to me, s to the n, plus c n minus 1, s to the n minus 1, plus da da da, plus c2s squared, plus c1s, plus c0, all right? That is the characteristic polynomial. I don't know what the coefficients are right offhand, but actually I can prove a little bit about it, as we'll see. But before I do that, I should, take care of an item here. Because one of the things we're going to do, which is probably new to this course, and you probably haven't thought too much about before, is we're going to define P of a linear transformation. So what should that mean? Well, let me divorce it from the thing right above it, actually. Let's let G of little t be, I don't know, C0 plus C1t plus da 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 plus ck t to the k, all right? then if we take G of a linear transformation, I guess I'll use big T for lack of imagination here. That means C0 plus C1 big T plus dot 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 plus CK T to the big K. Now what does that mean though? Like what is T to the 0 equal to? What is T to the 1 equal to? What is T squared equal to? What's all this mean, you know? So T to the 0 is by definition the identity on V. T to the 1 is, well, T. T squared is T composed with T. And T to the power K would be like T to the K minus 1 composed with T. And that's good for any K in the natural numbers. So we define powers of the operator in terms of like composition. Yeah.
I was going to ask if this could be extended to other integers or even real numbers.
Well, I don't know. Would it make sense to have K a real number? Well, that's an interesting question. I don't have an answer to that right offhand. I mean, even, I would say in the context that if the mapping was invertible, right? If the mapping was invertible, then I could even think of a meaning for negative powers, right? It would be powers of the inverse of the map under composition, perhaps. But, you know, what is T to the 1.5 power? I don't know. Make a Taylor series? I'm not saying that doesn't make sense. I'm just saying that it's not something I'm covering at the moment. So I'll save that one for the final. So here, we'll call it Joshua's problem. So here. That sort of thing leads to like the gamma function and weird stuff in the context of scalar. You know, like what's the extension of the factorial for non-integer values? The answer is it's unpleasant. So I'm guessing that maybe, let me shut up. All right, so example. You're like, what, an example? No way. All right, here we go. No, really, an example. So T of xy equals to minus yx for all xy in R2. All right. So here, A, we can make the standard matrix, which is just, you know, let's see here, 0, minus 1, 1, 0, I think, right? Sorry. So what's the characteristic polynomial in this case? P of S would be the determinant of, you know, A minus lambda S, which is minus, oh my bad, my lambdas are showing, minus S minus 1, 1 minus S, which I think is S squared plus 1. So the characteristic polynomial for this 2 by 2 matrix is S squared plus 1. Does this matrix have any eigenvalues? So nope. Cannot factor over the reals. So if there are no eigenvalues, there are no eigenvectors. This is an example of a matrix which is not diagonalizable.
Are we not considering complex numbers at the moment?
Not yet. And it will never be the case that a complex number is an eigenvalue for a real map.
Oh, right.
Yeah. There is something called the complexification of the map, which is an extension of the real map to a complex space. And then there you can find a complex eigenvalue. And that actually, the full discussion there leads us to what I call the real Jordan form. But anyway, that's the head of the story. Now, if we change the context, if we instead say, you know, T is a mapping, you know, from C2 to C2, right? Same definition, then all of a sudden we have, you know, P of s equals to s squared plus 1 is equal to s plus I times s minus I. And of course we get, you know, eigenvalues lambda equals to minus I or I for this map. So this same formula would be diagonalizable over the complexes, but not diagonalizable over the reals. They are different mappings, right? One is a mapping from R2 to R2. The other one's a mapping from C2 to C2. These are different examples. There. Here, let me make it even more clear. Not the same example. So, but something really neat happens here. What happens if we look at, and so what should P of A mean, by the way, guys? P of A should mean A squared plus the identity matrix, right? So like, I haven't made that definition formal, but in the same way that it defined the polynomial of an operator, we can define the polynomial of a matrix. We just plug the matrix into the polynomial. What happens with A squared here? Well, if you work it out, you get minus I. So we get minus I plus I, which is 0. So this exemplifies what's called the Cayley-Hamilton theorem. So this is the Cayley-Hamilton theorem in action. The Cayley-Hamilton theorem states that if you take the matrix and you plug it into its characteristic equation, it's identically 0. This is not part of example 2, although it's still true for example 2. This is actually a part of example 1. Okay, I'm making meaningless, you know, somewhat meaningless demarcations. Example 2. So that's one way a transformation or a matrix could fail to be diagonalizable. You just don't have eigenvalues in your field. All right, the characteristic equation can't be solved over your field. That's one thing that can happen. Another thing that could happen is, for instance, if we look at the set of quadratic polynomials, and we look at, this is one of my favorite examples, differentiation, right? If we look at T of ax squared plus bx plus c, we get, of course, 2ax plus b, which means that we have a, you know, with respect to the usual monomial basis, I get 0, 2, 0, 0, 0, 1, 0, 0, 0, if I'm using basis beta x squared x 1. So the decreasing monomial basis here. All right. Having graded your mission 3, some of you need to be like way more careful about that. Because, yeah. Anyway. So there it is. What are the eigenvalues? So, what's that? You're undoing it. Okay, so we got the determinant of minus s 0, 0, 2 minus s 0, 0, 1 minus s. This is an easy determinant to calculate. It is minus s cubed equal to 0. Yeah? So there is one eigenvalue. It's just 0. So we have lambda equals to 0 with what's called algebraic multiplicity 3. How many eigenvectors do we have here? Well, the eigenvectors defined here are the things in the kernel, right? What's in the kernel of the differentiation map? It's just the span of the constants, right? That's what we would call the eigenspace with eigenvalue 0. The eigenspace with eigenvalue 0 is just the kernel in this case. And as you can see, there's not enough eigenvectors, right? So this matrix is not diagonalizable. Because if it was diagonalizable, notice that whatever is on the diagonal must be eigenvalues. Think through it, right? But we know that the eigenvalues are 0. And we know that the only eigenvector with eigenvalue 0 is just 1. So I can't make an eigenbasis. I don't have enough vectors. Right? I need 3. I only got 1. So this matrix is not diagonalizable. All right? So here's, this is the problem, is how do we overcome this problem of these matrices not being diagonalizable? Like, what can we say then? All right? Well, let me just say a slightly more positive thing. One thing I can say is that if the matrix or the transformation is invertible, then 0 is not an eigenvalue. Can you guys see what that is? I shouldn't even need to write anything on the board. We should be able to talk about that one with just words. If a matrix is invertible, its kernel is what? 0. But the kernel is the set of 0 eigenvalues. Eigenvectors with eigenvalue 0, right? Because to say an eigenvector has eigenvalue 0 is to say that t of x is 0 times x, which means that x is in the kernel. So if it's invertible, it can't have an eigenvector with eigenvalue 0. So that gives us a theorem that if a matrix or a transformation is invertible, 0 can't be an eigenvalue of it. But you can say more than that. You can say if a matrix is invertible, well, there's more you can say, but I think I think that's your homework. I won't say that. Proposition, let me be careful. It's very easy to stumble into your homework if I'm not careful. Proposition 5.111, if you have A in Rn by n with n odd, then there exists at least one real eigenvalue. I mean, that's kind of redundant, but I'll just say it for emphasis because perhaps you talked about complex eigenvalues for real maps in your previous course, and that's fine. I will talk about that in like differential equations, for instance. But I'll try to explain more about how that's an abuse of language as we go on in here. On the other hand, if I've got an n by n complex matrix, then there exist n eigenvalues, possibly repeated. How do I know that? What is the characteristic polynomial? It is an nth order polynomial equation. What does the fundamental theorem of algebra say? It says a nth order polynomial equation over the complex numbers has n solutions, possibly repeated. So this is a direct consequence of the fundamental theorem of algebra. That's why working over complex numbers is so much nicer. All right. So one of the other things we can say is that the determinant of A is equal to lambda 1, lambda 2, lambda n, provided A has eigenvalues, lambda 1 through lambda n, possibly repeated. How do I know that? If you have eigenvalues 1 through n, right? Then that means that P of S can be written as what? Excuse me, minus 1 to the n times S minus lambda 1 times S minus lambda 2 times S minus lambda n. Why can I say that? Factor theorem, right? Each eigenvalue is a 0 of the characteristic polynomial. So that means I can factor out S minus lambda I for each one. What happens when you multiply this out? You have minus 1 to the n, and you've got minus 1 to the n times the product of the lambdas. So I guess to be careful, all this calculation so far does is show you that you've got, minus 1 to the n, s to the n, plus dot, 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 dot. Eventually, you've got your constant term here as the product of the eigenvalues, right? I guess that doesn't really show that the determinant of A is the product of the eigenvalues. But how do I know that the determinant of A is the product of the eigenvalues? Remember, it's the determinant of P inverse AP, where we can make P equals to V1 Vn, where A Vj is equal to lambda J Vj, right? So if I do that calculation, then when I calculate P inverse AP, what do I get? I get well, goodness gracious, I'm just going to write it down here. We get lambda 1, lambda 2, da, 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 lambda n, like that, which of course is so there's two things I'm saying here. The one thing I'm saying, these are really disconnected. So the one is that the determinant is the product of the eigenvalues. That is clear if you have n eigenvalues for an n by n matrix, right? Possibly repeated, but what I mean by that is that I have at least an eigenbasis with respect to these eigenvalues. Then I can do this calculation. On the flip side, if I look at the characteristic polynomial in such a case, it must be that the constant term is the product of the eigenvalues. So, I mean, sorry, I'm getting off track here. Let me get back on track. All right.
I'm trying to remember for 221, if you have a matrix that's greater, that's greater dimensional to.
If you have a what?
If you have a 3 by 3 matrix, if you have it in RAF form, you just take the product of the diagonal to find the determinant, right?
If the matrix is upper triangular, or if it's lower triangular, or if it's diagonal, then the determinant is just the product of the diagonals.
Okay.
Maybe that's what you're thinking of.
Yeah, sorry.
I mean, we have a dozen different determinant simplification rules that are based on like the interaction of elementary matrices and the determinant. But I don't know. I mean, I guess you can use those, but I'm not sure they matter too much for our current purposes. All right. So let me show you where we guys are. So we're in chapter, come on, notes. Chapter 5. I'll eventually get there. So we've looked at this example, looked at that example. I talked about that. We talked about this. I just walked through part of that. I'm not entirely sure that proof is right. I mean, you can be skeptical of the notes. If you think something's wrong, let me know. It's possible. I do make mistakes. But what's coming up here, which I really wanted more time for, but I just have to admit I lost some time to the printer today. It's all I have. And come on. So this result's simple. If we have an eigenvector and it's an eigenvalue for A, then it's also an eigenvector for A to the k, because you just keep applying the eigenvector condition over and over again. As you do, you pick up a power lambda each time, so you get lambda to the k But this being equal to that makes V an eigenvector for a to the k with eigenvalue lambda to the k. All right. And we were just talking about the upper-lower triangular matrix thing. So like you've seen this in the examples already. 0 and the derivative operator on the diagonal. Those are the eigenvalues, if you think about it. This right here is interesting. For a 2 by 2 matrix, we have these really cool formulas. The determinant is the product of the eigenvalues. The trace is the sum of the eigenvalues. And so we've already worked that out. But if you look at the determinant of this, we get that polynomial. And then I just calculated completed the square and, did the usual calculation there. And if you add the plus and the minus roots, the discriminant term cancels out, and you just get a plus d over 2 plus a plus d over 2, which is a plus d, but that's also the trace. So what's interesting is these formulas, that the determinant's the product of the eigenvalues, and the trace is the sum of the eigenvalues. This continues to be true even when the matrix is not diagonalizable, provided that it actually has enough eigenvalues. Like example 1, where we have no eigenvalues, that also gets repaired, but it gets repaired from what's called the complexification. So the next thing we need to talk about, and obviously I'm out of time today, but next time I will prove to you that if we have eigenvectors with distinct eigenvalues, those are linearly independent. So here's the proof for 2. You just assume they're linearly dependent, like this, right? Then that gives us this equation. But then if we solve for, but we can replace, we were assuming that what was kv2. So if I put that there, then I get k times lambda 1 minus lambda 2 v2 equals 0. But the thing is, these are distinct, so that's non-zero. I've got non-zero times vector equal to 0, but basic vector space algebra means that means v2 is 0. But v2 is an eigenvector, it can't be 0, right? So that proves that if you have 2 eigenvectors with distinct eigenvalues, they must be linearly independent. So next time we'll look at an incredibly far-reaching generalization of this result that will kind of definitively answer the question, when is it possible to diagonalize a linear transformation? At least it will give a positive criteria for when it is. And we're going to get back to that invariant subspace business. The proof is going to rest on one of those 5 parts of equivalence that we got.